let's start. I'm going to do some introduction in Portuguese so you all can understand, and myself, I can understand too. But Bill and David will not be able to understand, but then I explain to them. Queria dar as boas-vindas a vocês. Nós estamos dando início a uma sequência de palestras para comemorar os 100 anos da mecânica quântica, que parece tão distante de todo mundo, mas hoje já é, além de estar envolvida no seu celular, no GPS, no NMR que você faz, no hospital, nos sensores, em tudo isso, está virando tecnologia palpável, como é o caso do computador, das comunicações. Então, a ciência deixou de ser boa somente, excelente, para ser relevante. Pretende-se que resolva problemas. Então, a ideia de trazer 2 premiados com o Nobel em mecânica quântica, tópicos relacionados, e envolvido com aquilo que motivou o avanço tecnológico das coisas, é para motivá-los, e precisamos mais gente nessa área, né? Tá certo? E para alertar que ciência não é só para o cientista. O cientista não faz ciência só para ele, né? Ele faz para uma sociedade enorme. Então eu vou rapidamente, now I'll flip to English. I will do my best, and I know that many of you can understand my English because it's macaronico. And I will explain what we're doing here today. So first of all, the celebration of quantum is already started. We are just coming from the Academy of Vaticano, where they gave a very important kickoff on the direction of show that quantum mechanics is an important concept, even for non-physicists, right? And there will be a very nice statement about that. And I encourage you to get in the homepage of the Vatican Academy of Science and read it, because that was done by more than 50 scientists deeply involved in this field. Okay, so we have, I'm not going to do a formal introduction, because if you type William Phillips or David Weiland, you go directly to the Nobel page, and they describe it much better than I could. Who are those guys? Okay? But maybe I know those guys better than the Nobel Committee. Both of them are good friends of our institute. They used to come here often. David came on the 90s, and Bill is coming basically after I got here. The first year he came. And amazing that they work in different fields, as you can see. And the only paper they have together was done in São Carlos. Right? So it is a good pleasure to have both. They never decline the invitation to come to our institute. And they know the importance to speak to you, more to visit me. Today we have 2 persons, which I'm going to call 2 states. The first state is called David. The second state is called Bill. And you know, one of the main characteristics of quantum science is uncertainty. You came here today to see David, and you're going to end by seeing Bill. This is natural of quantum science. But let me elaborate a little bit. You see, quantum is very famous to superimpose life and death, cats, but we're going to superimpose Bill and David. And when you have superposition of 2 states, so this is a system with 2 possible states. We cannot have others speak. It's either David or Bill. 2 states. We call this in quantum mechanics 2-state system. Can either be one of them, but you don't know who. And because there is a good interaction, our field is making them to interact, they are in a superposition. So Bill and David, actually, we don't know yet who they are, and they are in a superposition. On the top of the oscillation of the superposition is Bill. On the bottom is David. And it turns out, as we keep this interaction, they're going to oscillate between being David or Bill. People call other things, they give you fancy names, but this is Bill and David state. So in between the oscillation, you see, it is a confusion. We don't know who it is. But if we are lucky, and if we observe the system in the top or in the valley of the oscillation, we're going to collapse either Bill or David. This is called the collapse of the wave function. So now we're going to try to do the collapse. So these is two girls that are trying to understand the quantum mechanics. They are carrying cats. You know, poor girl thought that she could take a cat home and do an experiment to make sure it's not exactly like that. You cannot kill your cat and wait sometimes to come back to life. It doesn't happen. If you see the cat, it's either dead or alive. Okay, so the girls are going to do the experiment, and we're going to do the experiment as well. After we do the measurement, which you all helping to do, when you enter in the amphitheater, we were starting to do the measurement. You start to observe properties. Oh, but that's computer of Bill. Oh, David is sitting in the chair. Those are details of the quantum measurement. Okay? So we did the measurement. You came, the sun was bright, and we start to observe. Each of you start to observe. But at the moment, until we click and find who is really here, we don't know. It can be either. And now we're going to do it. Oh, and after we have done, we found that by lucky, we got a pure state. So, Bill, we collapse on you. But don't get disappointed, because the interaction continues. And in the case of Bill and David, the oscillation between being the Bill or being David takes 24 hours. So now that we did a measurement, this is very important. You're laughing, but this is the way we do many things in quantum. Oh, David is going to speak about flipping things by pi phase. We go from Bill to David. If you wait long enough and do another, and then we mix again, we're going to go home, continue the interaction, and then tomorrow, 24 hours, we're going to go back. But we're not going to need to do this measurement again, because now we understand that we made one, and then we let the system evolve again, and then we're going to do a second. And I guarantee to you, tomorrow will be David. So tomorrow we have the talk of David. And this happens in quantum mechanics. We could not tell exactly who will be the first to speak, because until you start to get in here and people start to prepare, the measurement was not concluded. Now that we collapse in Bill, we connect again and pray God that everything is going to work. And if everything starts to work, we're going to pass the word to Bill.
Well, remember, we're going to have questions during the talk. Well, thank you. Well, thank you very much for that kind and amazing introduction. First, I want to apologize to everyone. While we were together at the Vatican, I caught a cold, and I'm afraid that my voice hasn't really recovered yet. So I hope that the stress on my voice does not make it too hard for you to understand what I'm saying. I'm also going to apologize because I think that the talk is too long. It took us too long to get the computer working, so maybe I'll try to skip a few things. But anyway, I'm going to talk to you about the revolutionary quantum reform of the metric system. And I'm from a place called the Joint Quantum Institute, which is joint between the National Institute of Standards and Technology and the University of Maryland. And I'm part of the Laser Cooling and Trapping Group, of which Gretchen Campbell is the leader. And I want to emphasize again what Vanderlei said, that you should think of questions. And if you ask a question, you will get a prize. And I think I may ask Lucas to give out the prizes, because it's going to be hard to do. We may have to pass the prizes around. Any question is okay, except for what is the prize? So, what is this revolutionary change to the metric system? Well, as people have said over the course of history, that science is about what you can measure. And if we make measurements, we have to express those measurements in some kind of units. And the international community has agreed that we are going to use what we call the metric system, which is known formally as the International System of Units, or the SI. So whenever you hear me say SI, I'm talking about the metric system, the modern metric system. And what I'm going to tell you about today is that recently we have undergone the biggest revolution. Well, first of all, the metric system started during the French Revolution, which was near the end of the 18th century, and we are now experiencing the biggest revolution in the metric system since the French Revolution. And the International System of Units today has 7 base units: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. And the definitions of all of those units are now based on some constant of nature. That is, we define what we mean by a meter or a kilogram or a second by defining, fixing the value of a constant of nature. Now, to understand how this is possible, I'm going to talk about one of the most important units that we use, the unit of time. And with apologies to Stephen Hawking, I'm going to bring you my version of a short history of time. Since people have started to talk about seconds, the definition of a second was that it was a fraction of a day. A day has 24 hours. There are 60 minutes in an hour, 60 seconds in a minute. So a second is the length of one day divided by 86,400. That seems very easy, very intuitive. The trouble is that for more than 100 years, we have known that the length of the day changes. The tides slow down the rotation of the Earth. Earthquakes, changes in ocean currents, change the angular momentum of the Earth, and that means that the rotation has to change to compensate for that. So we learned this by having clocks that were better than the rotation of the Earth. One of those kinds of clocks is an atomic clock. This is the first atomic clock. It actually used a molecule rather than an atom, an ammonia molecule. In 1949, this first atomic clock was better than the rotation of the Earth. Today we use cesium as the atom that keeps time, and the first cesium clock was made in 1955 in the UK at the National Physical Laboratory. So in 1960, the international community decided they would redefine what the second was. Instead of being a fraction of the mean solar day, the second was going to be something else. And we now had the technology to do much better than the rotation of the Earth. We had atomic timekeeping. For more than a decade, we had atomic clocks that were better than the rotation of the Earth as timekeepers. And so in 1960, they redefined the second to be a fraction of the year 1900. What were those idiots thinking? Now, it's true that the year 1900 doesn't change, but it's not so easy to measure it because it's already happened. And we are still suffering from what I consider to be the stupidity of this of this definition. So a few years later, in 1967 and 68, the General Conference on Weights and Measures finally redefined the second in terms of atomic time. And the second is now the duration of some 9 billion periods of the radiation corresponding to the difference between two hyperfine levels in a cesium atom. So let me explain what that means. So here's a cartoon of a cesium atom. It's got a nucleus. The nucleus is spinning, and because it's charged, it creates a magnetic field. That magnetic field is felt at the valence electron, which is also spinning and creating a magnetic field. And there's an energy difference to turn the spin of this electron in the opposite direction. And that energy difference corresponds to a frequency. And when you put in the right frequency, which is a little bit more than 9 gigahertz, then if the frequency is just right, then it will cause the electron to change its orientation. But if the frequency is not exactly right, then it won't. So you keep adjusting the frequency until you see that the electron has changed its direction, and then you know that you've got the right frequency. And by definition, that is the right frequency, because the way in which we define what we mean by a second is to define the frequency of this transition. Now, I think that it might be a good time right now to stop and ask if there are any questions. And remember, everyone who asks a question gets a prize, and Lucas, you're going to give them the prize. But you won't know what the prize is unless you ask a question and get the prize. So who has a question about anything you've heard so far? Yes?
In the previous slide, you said about hyperfine.
Yeah.
What is
Okay, what is hyperfine? Excellent question. So, so the question was, what do we mean by a hyperfine transition or hyperfine states? In atoms where the nucleus has a spin, not every atom has a nucleus with a spin, but a lot of atoms do. Cesium is one of them. Sodium is another one. Hydrogen is another one. Lithium is another one. Some of my favorite atoms. Because it's spinning, it creates a magnetic field. If you have a valence electron, an unpaired electron, that means that there's electron spin as well. So the nucleus acts like a little tiny magnet, and the electron acts like a little tiny magnet, and the magnetic field of the nucleus, as felt at the electron, is going to make it so that you have to add energy in order to change the orientation of the field. Imagine you had a compass needle and you wanted to change its orientation. You would have to do some work on the compass needle to turn it around. Well, it's the same idea. If I want to make the electron flip, then I have to do some energy, and that energy comes from microwaves. So hyperfine simply means the structure, the fact that there are different energy levels because there is a magnetic nucleus and there's a magnetic electron. So this guy gets prizes. So you have to come and give them. Oh, you're going to keep track of who gets the prizes? Boy, that's going to be hard.
we give it a prize.
Sure, give him the prize. Both prizes.
You can ask him to.
So now, now I'll tell you what the prizes are. The first one is a periodic chart of the elements, the best periodic chart that has ever been made. Of course, it's made by NIST, the place that I work. And the other one is a wallet card of the fundamental constants of nature. You've got the speed of light. You've got the hyperfine frequency of cesium. It's right there in the card. Planck's constant, all things we're going to be talking about today, the charge of an electron. So you get one of these as well. So those are the prizes. Who wouldn't want those? Now, you'll have to shout out your question.
Stand up and ask the question. Loud.
Ah. Excellent, excellent question. In fact, it's okay. Why cesium? So I'm sitting down because, you know, with this cold that I have, I'm a little bit not as strong as I usually am, and I don't want to collapse during the talk, even though Vanderlei talked about collapse. I don't think it would be a good idea if I collapsed during the talk. Okay, why cesium? We wanted to use an alkali. So you remember from your chemistry class in high school that on the left-hand side of the periodic chart, and if you ask a question, you'll have a periodic chart, are the alkalis, ones that have one unpaired electron. This makes it very simple. They have hyperfine structure, which is what we want, because otherwise we don't have a clock, at least not this kind of a clock. And cesium, being the heaviest of the non-radioactive elements, has the biggest hyperfine structure because it's got the biggest nucleus, and the electron is sucked into the nucleus further, so you get the biggest hyperfine structure. Why do we want the hyperfine structure to be big? If there's some effect that influences the hyperfine energy, then it'll be a smaller fraction if the hyperfine structure is big. Cesium has the highest vapor pressure of all of the alkalis. So when you don't have to heat it up very much in order to get some atoms. And we want atoms that are in a gas phase, because if they're stuck onto each other, that'll affect the frequency. So we want them to be floating freely in space. So we don't have to heat them up very much. For whatever temperature we heat them up, because cesium is the heaviest, it means it's not going as fast. Because for the same temperature, the kinetic energy of the atoms is the same, and kinetic energy is 1/2 mv squared. So if m is bigger, then v squared is smaller. So, and as you'll see, having the velocity smaller is a good thing, because if the atoms are going very fast, you don't have very long to look at them. And we want to look at them for a long time. So, so that's a good reason. The other reason, or one of the other reasons, is that it's easy to detect cesium atoms. It takes the least amount of energy of all the alkalis to pull an electron out of the cesium atom. So it turns out that when a cesium atom hits a metal surface, if what's called the work function, the amount of energy that's required to pull an electron out of the metal, if that's bigger than the ionization energy, the energy required to pull the electron out of the cesium, then the electron would rather be in the metal. So when it hits the metal of the right sort, then it sucks the electron out of the cesium atom, and now you've got an ion. It's electrically charged, and that's easy to detect. So all of these reasons were among the reasons why they decided to use cesium. And then it turned out that later on, when we learned other ways of doing things, cesium was still, by great good fortune, a wonderful atom to use. So make sure that that woman gets her prizes.
Oh, she's getting the best table of fundamental concept.
Okay, now the woman in the purple shirt.
So, but let's do one thing. Let's do a group of questions, and then let's view evolve a little bit. We want to understand why we don't need to measure anymore some of the constants. And then you need to let him go a little more. So one more question, then we move him a little bit, another ones, okay?
Okay, so
good? Don't worry.
Stand up and yell.
Is there any possibility that any ambient condition changes the way?
Right. So the question is it possible that ambient conditions can change this hyperfine frequency? And the answer is yes. So it turns out that the definition of the second that I gave you before is not the whole story. Because Einstein taught us in 1913 or 14, when he came up with his theory of general relativity, that clocks run slower when they are deeper in a gravitational potential. Nobody knew that before. So a clock will run slower at sea level than it will up on a mountain. Now, this didn't used to be a problem because the clocks weren't good enough, but today the clocks are amazingly good and they can tell the height difference of less than 1 centimeter. But when I first started working in this business, they couldn't even tell the height difference of 1 kilometer. And now they can tell the height difference of 1 centimeter. So the definition of the second includes that it should be at the mean value of sea level. Now you may notice that's a problem in today's world because sea level is changing because of global warming. So we haven't really figured out what to do about that. And that's going to be a problem for us. In addition, the frequency, the hyperfine frequency, is changed by the ambient temperature. So if you're in a room at a certain temperature, in a laboratory, the radiation that comes from everything that there is that's warm, we call that black body radiation, that can shift the frequency a little bit. That didn't used to be a problem either, but now that the clocks have gotten so big, so good, then we have to worry about that as well. And so the definition now includes what the temperature should be. So these are things we have to worry about. But now Vanderlei tells me that I have to move on. But make sure that that woman gets her prizes. Okay, let's keep going. So over time, these clocks, from the very first clock, cesium clock, kept getting better. So as we go down, the clock is getting better and better with time. It's kind of a Moore's law. That is, it's getting better exponentially. But in the 1990s, the clocks were about good to a part in 10 to the 14. Now think about that. A part in 10 to the 14. That is a part in 100 million. It's the most accurate measurement of any unit of the metric system there is. But we were not satisfied. We wanted to do better. And in order to do better, it turns out that we needed to make the atoms move more slowly. Remember, I talked about how we wanted the atoms to be slower to begin with. And the trouble is that we have to heat them up a little bit just to get any gas atoms at all. And then they're moving at whatever that thermal velocity is, which is more than 100 meters per second. And that was the thing that limited the performance to a part in 10 to the 14. So what happened was we developed techniques to cool down the atoms, which is to say make them move more slowly. And those techniques allowed us to push the accuracy of the clocks almost another 2 orders of magnitude to get to parts in 10 to the 16. So that's what has happened, as you see here. This was all due to using laser-cooled clocks. Now, what do I mean? What am I saying about laser cooling? I'll explain that in a moment. Why do we need laser cooling? Well, I told you that we wanted to look at these atoms for a long time. That's what this first idea is, that if we can't look at the atoms for very long, then the range of frequencies over which the microwaves will cause the spins to flip will be broader. And if we can look at them for a really long time, then that range of frequencies is narrower. And we need to find exactly the middle of that range, and it's easier to do if that range is narrow. So we want to have the atoms go more slowly. Also, there are Doppler shifts. So you've heard about Doppler shifts, right? If a train is coming toward you and blowing its whistle, the frequency will be higher. The pitch of the train whistle will be higher if it's moving toward you than if it's moving away. Well, the same thing happens with the atoms. The frequency of the atoms is changed depending upon whether it's moving toward you or away from you. And we need to get rid of that. And there are a lot of tricks for getting rid of it, but they aren't perfect. And so we need to make the atoms go more slowly to make that effect smaller. In 1905, Einstein taught us that moving clocks run slow. It's a very small effect, but for the precision that we want, we have to take that into account, and there's no tricks to get rid of it. The only way we can get rid of it is to either measure the velocities, which is hard to do, or make them be really slow. And so we embarked on a program to make these atoms go colder, to make them go colder. And here's how it works. Here are the atoms. These green things are cartoons of the atoms, and there is some frequency of light. Light is just like microwaves at a higher frequency. Some frequency of light that these atoms will absorb. If they are sodium atoms, they will absorb light that has the color of these yellow street lamps that you see. The color is determined by the frequency of the light. And if the color isn't just right, and I mean it has to be really just right, it has to be within a part in 100 million, or it won't, or the atoms will not absorb it. If the color is just right, the atom will absorb the light, and the light will push on it. Now what we do is we arrange the frequency so that it's a little bit below the frequency that the atom likes to absorb. And when the atom is moving toward the light, the Doppler shift makes it appear the frequency is a little higher than it would be if the atom was at rest, which means closer to the frequency the atom likes to absorb. So this atom will absorb light from this laser beam and slow down. This atom, on the other hand, will not absorb very much light from this laser beam because it's going in the wrong direction, and the Doppler shift is in the wrong direction. This atom will absorb light from this laser beam instead, and it will slow down. So atoms will slow down no matter which way they are going because of the laser beams coming in from different directions. The idea of this came from a guy named Dave Wineland, from whom you're going to hear tomorrow, okay? And his colleague Hans Demelt, and there were also two guys named Ted Hench and Art Shallow, who in 1975 came up with this idea. Every one of those guys got a Nobel Prize for something else. So that gives you some idea of how smart these guys are. That this huge, amazing idea is not the thing they got the Nobel Prize for. Okay, so here's a picture in our laboratory of atoms being cooled in 3 dimensions. I just showed you a 1-dimensional version. So there are laser beams coming in from all directions, and these atoms get cold. How cold do they get? Well, you could go through the theory, which I'm not going to do, and you find that Boltzmann's constant times the temperature, that's the thermal energy, is equal to the energy width of the range over which the atoms will absorb light. And when you figure that out, for sodium, that's 240 microdegrees above absolute zero. That's really, really cold. The coldest temperature you would ever encounter on the face of the Earth is about 185 degrees above absolute zero. Someplace in Antarctica in the winter was the coldest temperature they ever found. I'm talking about 240 microdegrees above absolute zero. This is incredibly cold. And so we thought this was a really good idea to make the atoms that cold. And so by looking at how fast the atoms are going in here, we determined that, and the first measurements were made by Steve Chu at Bell Labs, and we made similar measurements a little bit later, and other people made measurements on cesium, and everything was great. It looked like the theory was predicting what the temperature should be. But then we started to measure other features of the laser cooling process, and it wasn't adding up. You know, I wish we had some laser cooling going on in here because it's really hot. Of course, I think this is because of all of you. Because, as you probably know, each one of you is putting out 100 watts of heat on average. And that really makes a room quite hot. So it's because you all are so hot that I need to make adjustments. Okay, so we made more careful measurements of the temperature. What we decided to do was to have the atoms here and then turn off the laser beams and allow the atoms to drop to another laser beam. And the idea is that if the atoms were going really fast, we would get a peak early, and if the atoms are going very slowly, then it's just whatever time it takes for something to drop that far. Here's what we expected to see. Here's what we actually saw. Everybody in the world who worked on this field believed that the temperature could not possibly be any lower than 240 microkelvin, as shown in this curve here. We were seeing a curve that looked like it was 40 microkelvin. In other words, 6 times colder than what everybody in the world said was possible. Do you know how exciting it is to learn something that is different from what everybody thinks? This is the dream, I think, of every scientist, to see something that is completely different from what people think is true. And believe me, it was pretty exciting. Well, at the beginning, we looked at it and we said, we must be making a mistake. And then we worked and worked, trying to prove that we had made a mistake. And when we couldn't prove that we'd made a mistake, then we finally realized that we had discovered something new. This is one of the reasons why it is so wonderful to work in science, because every day we're learning something new. And that's one of the most exciting and wonderful things you can do. Well, I wish I had time to tell you why this works, but I don't. But with the new there was a new theory, so that's what I forgot to say. Some of our friends who were theorists came up with ideas that explained what was going on. We did some more experiments to test whether the theories were right, and then, guided by that new theory, we were able to get cesium atoms, and this was very important because, of course, cesium atoms are the ones we use for atomic clocks. We were able to get cesium atoms down below 1 microkelvin, below 1/1,000,000th of a degree above absolute zero. So instead of using cesium atoms that were at a temperature of about 350 degrees above absolute zero, we were using cesium atoms that were 1/1,000,000th of a degree above absolute zero. And that made most of the problems having to do with the motion of the cesium atoms go away. So now we have clocks that look like this. There's Don Meekhoff and Steve Jeffords, and they take cold cesium atoms and they toss them up in a vacuum, and they come back down after a second. So instead of having maybe 10 milliseconds, you have a whole second for the atoms to come back down, and they make these clocks work to within a few parts in 10 to the 16. So let's stop and have a few more questions. Yes? Louder.
You expand your question already.
Hello. In the previous slide, it was right about gaseous molasses. Why
yeah.
molasses?
Yeah, right. So why do we call it molasses? Because the laser cooling works so well that the atom cannot go very far before the laser cooling stops its motion and has the atom going in a different direction. So the atoms feel as if they are in a viscous fluid. And molasses is this, I guess you know what molasses is, it's a viscous sugar solution. And so the motion of the atoms in the light field is very similar to the motion of a particle in a viscous fluid. So all the way in the back, you stand up and shout. Okay, so how about if he should get a prize, but I think what we'll do is we'll wait a little bit until a little bit later in the talk to address that question. Okay? Yes?
My question
Right, so the question is, how do we know that the electron spin has flipped? Well, in the old days, by which I mean before lasers, you would put the atom through an inhomogeneous magnetic field. And electrons that were in one direction would be deflected one way, and electrons that were in the other direction would be deflected the other way, and that way you could tell. Today, we just shine a laser on the atoms, and the ones that are in one direction will light up and scatter lots of light from the laser, and the ones that are in the other direction will do nothing. So that's the way in which we tell which way the electrons are pointing. Yes, all the way in the back in the green top. No. The woman back there. You are not wearing a green top. Oh, what's my biggest dream now? Well, of course, it changes depending upon how I'm feeling. So one dream that I have is to make a quantum computer that can solve quantum mechanical problems that I cannot solve today. So there are all kinds of wonderful and interesting problems that are so difficult that modern computers cannot solve them. But a quantum computer, if we can make a good enough quantum computer, would be able to solve these problems, and that's one of the dreams that I have. Okay, so in the pink shirt, but yell. Not exactly. So the question was, do we have to measure repeated transitions? What we are measuring is not the rate at which the transitions are made. What we're measuring is what microwave frequency can make the transitions happen. So it's not about how fast the transitions happen, it's about whether they happen or not. If we use a weaker microwave, less power in the microwave, then that will make the transition happen more slowly, but it'll still happen only at the frequency of the microwaves. So now the way it actually works is that we repeatedly do the experiment with different microwave frequencies, and we see how much, what fraction of the atoms have their spin flipped, and when we determine the frequency that makes the maximum in how the atoms' spins are flipped, then that's the frequency that we want. Okay, I think maybe we should go on. And hold your question. If you have a question, remember what it is, and we'll try to do it at the end. Okay, let's keep going. Okay, so now, here is one of the key things that I want you to understand about this lecture. We went from having a completely classical object, the Earth, as being the standard of time, to a quantum object, and looking at a quantum transition in an atom. So this is the nature of the change in the metric system, where we went from a classical definition of time to a quantum definition of time. Okay, now what we're going to do is we're going to go on to, if I can find where my cursor is. Okay, here we go. So now I want to talk about length. Historically, length was really important because it had to do with commerce, and the early approach to length was to use the human body as the standard of length. So a foot was a foot, and a fathom was the distance between the ends of your fingers. Now, this was really convenient because you always had the standard with you. The trouble was that everyone was a little different. So that if you were buying fabric from a short fabric merchant, you might not be getting the amount of fabric you thought you wanted, And if you got fabric from a tall fabric merchant, maybe that was a really good deal. So how do you deal with that, that problem? Well, one way is to make the particular body be a very specific body, usually the body of the king, or in the case of the ancient Egyptians, the body of the pharaoh. So they defined a thing called the royal cubit, which was related to the distance between the pharaoh's elbow and his fingertips. And I think the royal cubit added a hand to that. But in any case, this became the royal cubit. Now the trouble is that the pharaoh isn't always available. You know, he's off, you know, giving interviews or whatever. And so what they did was they made an artifact, a stone that was as long as the pharaoh's forearm. And then the engineers who were building pyramids out in the field would have wooden versions of these things, and they would use them to do the building. These people were very serious about their metrology. The people who used these wooden standards in the field were required to calibrate them against the stone standard every month on pain of death. So they really took metrology seriously in ancient Egypt, and as a result, the pyramids are made to very exacting standards. Similar artifacts were all over Europe, for example. Here's an example of one set into the stone of the city hall, and you can see that this particular fathom is quite generous compared to this tourist who is measuring herself against it. But this, if you went to a different town, you would have a different length, and this was causing a lot of problems. So along comes the French Revolution. And the French revolutionaries wanted to create a system of measurement that would express the ideals of equality that the revolution was about. So they decided to have a new standard of length called the meter. And the meter was 1/10,000,000th of the distance between the pole and the equator on a meridian that goes through Paris. And the idea of this was to create a system of units that would be good for all time and for all people. And in this medal that they cast to commemorate that idea, you see a mythological creature measuring the earth. And that's what they did. They sent out surveyors to measure the earth, the distance between Dunkirk and Barcelona, and then they extrapolated to the rest of the earth. And they came back with these new measurements. But of course, redoing that measurement is very difficult. It took them years to make that. So what they did was they made an artifact again, just like the ancient Egyptians did, that was based on this survey that they had made of the earth. So this is called the meter of the archives. End to end, it was 1 meter long, according to the measurements of the surveyors. A few decades later, the countries of the world got together and decided to adopt and support the international metric system, and they made a new international prototype of the meter, where the meter was the distance between 2 scratches on this rod. But at the same time, people were learning how to measure distances with light. This is a cartoon of an interferometer that interferes beams of light, and the beauty of this interferometer is that if you move this mirror by just 1/4 of a wavelength of light, so that's less than 200 nanometers, less than 2/10 of 1/1,000,000th of a meter, then this spot changes from dark to light. The scratch that is on the meter bar is 20 micrometers wide. And you can easily measure things that are less than 2/10 of a micrometer. So what it meant was that you now had a technology that was much better than the very definition of length. So people started to measure length in terms of optical wavelengths of light. And so finally, in 1960, they redefined what they meant by a meter. The meter was now defined as being a certain number of wavelengths of a light from a krypton lamp. So you put krypton gas in here and excite it with some electrical current, and some yellow light comes out, and that was the standard that defined what we mean by a meter in 1960. But 1960 was the year the laser was invented. And soon laser light was much better than the light coming from the krypton lamp. This laser had its frequency, which is to say its color and its wavelength, locked to a certain transition in molecular iodine, and everybody was using these lasers as the standard of length. So when people reported how long something was, the dimensions of anything, they would report it in terms of the wavelength of this laser stabilized to a molecular transition in iodine. And so, since everyone was using this new technology, it was clear that the definition needed to be changed again. And the most obvious thing would have been to redefine the meter as being a certain number of wavelengths of this laser light. That would have been the obvious thing to do. Fortunately, they did not do the obvious thing. Instead, they did something beautiful and brilliant. They defined the speed of light. The new definition is that the meter is the length that light travels in a certain fraction of a second. And this number here is the speed of light. This definition defines the speed of light. It defines what we mean by a meter by defining the speed of light. And the beauty is you've got this universal relationship that the speed of light is equal to the wavelength times the frequency. So it means if you've got any light at all and you can measure its frequency, if you define what the speed of light is, you immediately know what the wavelength is. So you've got a ruler that can measure anything you want as long as you've got light whose frequency you can measure. And if somebody makes a better laser that has a purer light, then this definition is still good. If somebody figures a better way of measuring the frequency of light, the definition is still good. These guys did exactly that. Jan Hall and Ted Hench made lasers that were better, and they made ways of measuring the frequency of those lasers that was better, and that was already incorporated into the speed of light, into the definition of the meter before they got the Nobel Prize in 2005. So here's something really important. We went from a classical object, an artifact, to a quantum object, an atom that's emitting light of a certain color, to a universal constant of nature. And the beauty of this is that we should never need to change the definition again. No matter what happens in the future, improving the technology, the definition that we have of the meter should still be good. So let's pause for a few questions. Yes, stand up and yell. Right, well the question is, how are quantum computers different from the ordinary computers that we have today, and what kinds of problems can they solve? Come tomorrow and listen to the talk by Dave Wineland, and he will explain everything, okay? All the way in the back, and then you're next. Yeah. Okay, so I think the question is, what is it that makes those atoms rotate? Is that the question? Why are the atoms rotating? Okay, so the atoms are made up of electrons and protons and neutrons. Those things each have a spin. They're all spinning. And that's just part of their nature. None of them ever exist without spin. None of them ever exist with a different spin from one another. They're all protons are the same as all other protons. All electrons are the same as all other electrons. Now, when you put them together, if you put them together in pairs, so you've got a proton up and another proton down, they cancel each other out and that'll be zero. Same thing with neutrons. But if you have an odd number of protons or an odd number of neutrons, then you will have a net spin, and that's what happens in the alkalis, okay, at least in the non-radioactive ones. Okay, now there was a question somewhere over here. Yes? Right. Okay, so there's a number of questions there. So first of all, yes, we do it with lots of different atoms. Now, Dave Wineland, he can do it with a single atom. But it's the same problem, whether it's a single atom or whether it's a million atoms. We get a better signal-to-noise ratio if we use lots of atoms. I'm sorry? Well, if you're lucky, then having more atoms doesn't change anything. It'll be the same frequency because the atoms don't interact very much. Now, the problem is that with the cesium atoms, they do interact, and we have to worry about that. In the case of the single ion, the beauty is that there's just one, so you don't have to worry about the interactions. As far as the distribution, that is, some atoms might have different velocities, well, that creates some uncertainty in the, and that's part of what goes into the new uncertainties is those kinds of differences from one atom to another. Now, it turns out that the velocities are so small that it's essentially negligible for that. The collisions, on the other hand, that is not negligible, and you have to worry about that. So those are among the things that we have to think about. So here, yell. Yeah. Will you cover that, Dave? Why we need such precise clocks? A little bit, yeah. So one of the reasons we need such precise clocks is satellite navigation. Another reason we need such precise clocks is basic tests of the theories of nature. And Dave Wineland will talk about that more. I think we'll take one more question. Yes? Okay, so your question is this circular? That is, are we trying to define something by using itself? Well, it's true that we need time. We need the definition of time in order to have the definition of the meter. That was not the case when the meter was the distance between two scratches on a rod. But as long as you keep track of things, it's okay to first define what you mean by time and then use that definition to define what you mean by a meter. And in this case, we're not using the definition of the meter to define what we mean by a meter. We are using the definition of time to define what we mean by a meter. So the meter is just the distance light travels in a certain length of time. So time certainly comes in, but we don't have to use the definition of the meter in order to define the meter, so it's not circular. Think about it. Okay, so I think we go on. Vanderlei is getting nervous. Okay, so now, this definition of the meter is both brilliant and beautiful, even more beautiful than the definition of the second, because it involves this really fundamental constant of nature, the speed of light. On the 20th of May, 2019, we agreed to bring this same beauty to the definition of the kilogram and the ampere, the Kelvin, and the mole. So this is the real heart of the story. So why did we need to do that, and how was it done? Well, so in order to do that, let me give you a light history of mass. These are some stones that were used in ancient Babylonia as mass standards. One of these, I can't remember which one, is a shekel, a word you might have heard. And the trouble was, just like every artifact standard, there were differences in the artifacts from one place to another. So the French revolutionaries thought, let's fix this using this universal new measure called the meter. Let's call the new unit of mass the kilogram, and we're going to make the kilogram be equal to the mass of 1 liter of water, where a liter is a cube, a tenth of a meter on each side. Well, that's a pretty nice definition. Water is easy to get. It's universal. We now have this new definition of the meter. The trouble is, it's not that easy to put together exactly 1 liter of water. You know, the water has a meniscus, and it changes its density with temperature, and it wets some things and it doesn't wet other things, and it's buoyant because it doesn't have a very high density. So what they did was they made the best measurement that they could of what the mass of 1 liter of water was, and they made an artifact. See, a familiar story. They made an artifact, a platinum cylinder, and there I am holding that very artifact. That is called the kilogram of the archives. It was deposited in the archives of France in 1799 and became the standard of mass for all of France. And later, at that same international meeting in which they adopted the meter, they mandated a new kilogram should be made, and there it is. That's the international prototype of the kilogram. And the new definition was that the kilogram is equal to the mass of the international prototype of the kilogram. Pretty simple. But think about this. It is the 21st century. The unit of mass is an artifact, a piece of metal that was made in the 19th century, that was based on an object that was made in the 18th century. The fact that in the 21st century we are using technology that is 18th century technology is scandalous. And worse, if someone were to leave a fingerprint on that international prototype of the kilogram, all of you would lose weight, but not in a way that would affect your health in any way at all. So what can we do? Well, nobody leaves fingerprints on these things. They're very careful in the way they handle them, but it appears that the mass of the kilogram is changing just the same. Here is a plot. No, I haven't quite gotten there yet. Here is a plot that shows the mass of other kilograms that were made at the same time and distributed to all of the people, all the countries who signed the International Treaty of the Meter. They all got copies of the kilogram and of the meter for themselves. And then periodically they would compare the masses of these other kilograms, which were made identically to the international prototype of the kilogram, and this is the result. Some of them changed by 100 or more micrograms. Most of them changed by a few tens of micrograms. and they're almost all going in the same direction. And this makes you think that maybe the kilogram itself, the international prototype of the kilogram itself, is the thing that changes, but it cannot, because by law, it is always a kilogram, no matter what. Well, this scandalous situation had to be fixed, and we wanted to fix it in a way that was beautiful, in the same way that we fixed the meter. We're going to define a constant of nature. So which constant shall we define? Well, I want to remind you of what must be the most famous equation in all of history, E equals mc squared. What does that mean? It means the energy of an object at rest is equal to the mass of that object times the square of the speed of light. Einstein taught us that in 1905. Planck taught us that the energy of, well, he didn't really believe in photons, but let's not worry about that. The energy of a photon, a particle of light, is equal to Planck's constant times the frequency of the light. Now, if we put these two equations together and solve for m, then we find that the mass, what is the mass? Let's say that I had an atomic nucleus and it emitted a photon in the form of a gamma ray, and I could measure the frequency of that gamma ray. Then when a nucleus emits that gamma ray, it will change its mass by this amount, and that amount is equal to Planck's constant times the frequency of the gamma ray divided by the square of the speed of light. Now, we can measure frequencies. The speed of light is already defined, so if we define Planck's constant, then that means we have a new definition of mass. Now, the fact is that we are not going to weigh photons. That's what this idea is about. We can, but we can't do it well enough. But here is a description of how we can use this definition to measure the mass of a single atom in kilograms. You're used to hearing about what the mass of atoms are in atomic mass units. Now we're going to get the mass of these atoms in kilograms using this new definition. So the idea is we've got an atom here at rest. We hit it with a laser, and one photon is absorbed by this atom. It takes it to the excited state, and because the photon carries momentum, the atom is now moving at a velocity that we can calculate from conservation of momentum. So we know what the velocity is. It's Planck's constant divided by the mass and the wavelength. We're defining Planck's constant where the wavelength is easily measured, and we can also measure the velocity using a technique that I don't have time to talk about called atom interferometry. And we solve for the mass, and this is the mass of the atom in kilograms. Now, if we could just multiply that mass up by a really large number, we could make it up to a kilogram. And we have a way of doing that. We compare the mass of that atom, probably rubidium, to the mass of silicon atoms. We take the silicon atoms and make a perfect crystal of silicon, turn it into a sphere. This is the most spherical object ever made on the face of the earth. It's out of round by a few tens of nanometers. And then it's a perfect crystal. We measure the crystal spacing using X-ray diffraction. We measure the diameter using optical interferometry. And now that means we know how many silicon atoms are in there. And we know the mass of each silicon atom because we can compare the silicon mass to the rubidium mass, and we know the rubidium mass in kilograms. So that's one way of doing it. The beauty of this definition is it doesn't tell us how we should do it. And there's another way, which I'm not going to take the time to tell you about, in which we use forces between current-carrying wires as a way of producing a force equivalent to the weight of a kilogram. And when, well, that's, I'm not going to tell you about all these things except for the fact that you have to use quantum ways of doing the electrical measurements. We're going to measure voltages using the quantum Josephson effect. We're going to measure resistance using the quantum Hall effect by Klaus von Klitzing. And there's a picture of one of these devices at NIST which allows us to realize the kilogram to about a part in 10 to the eighth, which is much better than the fluctuations we see in the kilograms due to whatever it is that's going on. The people who do this are really serious. They tattooed the values of Planck's constant onto their arms because they're really serious about metrology. And when laboratories all over the world agreed on what the value of Planck's constant was, because before you define Planck's constant, you do this experiment and it's a measurement of Planck's constant. When everybody agreed on what the value of Planck's constant was, they decided, the international community decided, to redefine the kilogram by defining Planck's constant. And I hope this will work. This is a movie that they showed after the unanimous vote of 60 countries from all over the world that we should make this change. So I'll hope that this works. If it doesn't, maybe I'll have to use a microphone. No, nothing's coming out. Okay, never mind. I think it's going to take too long to fix that. So those were pictures of people from all over the world saying how wonderful it was that we'd made this change that allowed us to have people being able to measure mass anywhere in the world with very high precision. You don't need access to an artifact anymore. You've got a fundamental constant, Planck's constant, that can tell you what a kilogram was. And the point that I want to make is that this is the way you ought to handle things between nations. 60 countries in the world unanimously agreed to redefine the kilogram, even though they all had different perspectives and we had very intense negotiations about what we should do. Everyone finally agreed. But that's not the end of the story. The ampere used to be defined as being the current that would produce a certain force between current-carrying wires. Now, the ampere is defined by defining the charge of the electron to be a certain number of coulombs, 1.6 times 10 to the minus 19 coulombs. So the ampere is now a certain number of electrons per second. The beauty of that definition is just marvelous because it goes to the microscopic idea of what electric current is. We don't actually count electrons, although we're working on it to do it better. What we do is, by virtue of the fact that we've got both the electron charge and Planck's constant defined, 2e over h, the Josephson relation, and h over e squared, the quantum Hall relation. This gives us hertz per volt, so you can convert frequency to voltage. This gives us resistance directly. So if you've got a standard of voltage and a standard of resistance, you've got all the electrical measurements you need. So that's the way we're using this to do electrical measurements rather than counting electrons. But maybe in the future, we will be counting electrons. The mole used to be the number of, the amount of substance that corresponded to a number of entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. Not anymore. Now it's just a number. This is Avogadro's number, and it's defined to be a certain number. The Kelvin used to be 1 over 273.16 of the triple point of water. Now it's defined by defining Boltzmann's constant. And I love this definition also because it tells us about what temperature is on the microscopic level. Temperature is about the energy of the constituents of the material, and Boltzmann constant is simply a conversion factor between the energy in joules and the energy in kelvins. Well, the French Revolution brought us the metric system. The Convention de Mètre, the International Treaty of the Meter, brought us an international agreement about units so that the whole world uses the metric system. And on the 20th of May, 2019, which is the anniversary of the signing of the Convention de Mètre, we had what I'm calling the biggest revolution in measurement since the French Revolution. And so this image of liberally leading the people means that we are finally free of artifact standards of measurement. And we've wrapped up the international system of units in this beautiful package that is realizing the dream of the French revolutionaries of providing a system of measurement good for all time and for all people. Except it seems, for time itself. Because our definition of time is tied to a specific atom, cesium, rather than to a fundamental constant. And these people, Anna Maria Ray, Junyi, and their colleagues, are now using a different atom, strontium, that gives an accuracy that is 100 times better than the best accuracy of the cesium atoms, 2 times 10 to the minus 18. Dave Wineland, in his laboratory, does even better. Parts in 10 to the 19, well, here, parts in 10 to the 19 for a single aluminum atom in a trap. And probably the definition of the second is going to change within a decade, but will it be the last change made? Only time will tell. But finally, one point. Quantum entanglement, one of the things that is part of the second quantum revolution that we talk about so much, something that is intrinsic to quantum information processing. Quantum entanglement is going to allow these atoms to achieve a precision better than what you would expect if we didn't use this strange feature of quantum mechanics. And so that's going to be part of the quantum future. There's going to be a redefinition. I don't know what atom is going to be chosen, but it's going to be better than what we have today. And whether it will be the last definition, I'm not at all sure. Only time will tell. Thank you very much. Thank you. Thank you very much. Thank you. So I guess we're going to have questions until Vanderlei tells us we have to stop.
Okay. We're going to have until I tell
So
let's move a little bit around.
and yell.
First, I would like to thank you for the presentation. It was wonderful. I love it. Everyone here loved it. I love your voice. Make her love like a documentary. My question is, how do we get the fundamental constants of nature that we use to define our measurements? Because I didn't understand if I got it right. I know the defending is more side from the beginners. And we are trying to define measurements by making some fundamental constants of the universe. But if we define them like we say, these are the last digits of these constants, we're not taking something from nature. We are like defining the last part of them, and then we get our measurements. But if they are not defined, how can we extract them from nature? Isn't like a red hole that we are entering?
Right. Okay, so the question is, how can we determine what is the value that we should assign to the fundamental constant if we don't already know it? That's sort of the gist of what you've asked. Let's take as an example the definition of the meter by defining the speed of light. The way they chose the value of the speed of light was by measuring the speed of light using the old definition of the meter and by measuring the frequency of the light. So what they did was they got a laser and they measured the wavelength of that laser relative to krypton, okay? Because krypton, the wavelength of krypton was the definition in the old way. So now they know what the wavelength of the laser is relative to the old definition of the meter. Now they had to measure the frequency of that laser. It wasn't easy. They had to start with microwaves and multiply the frequency of the microwaves up to the far infrared, and then multiply that up into the near infrared, and then multiply that up into the visible. And eventually they got the frequency of the laser whose wavelength they knew in terms of krypton. That gave them a measurement for the speed of light with a certain uncertainty. So what they did was they then fixed the value of the speed of light to a number that was the best measurement that they could have of the speed of light with the best techniques they had at the time, and then they decided that would be the new fixed value of the speed of light. So every time somebody makes a new definition, what they try to do is make sure that the new definition is within the uncertainty of the old definition. So there won't be any jumps in the definition. They failed to do that in the definition of the second in 1960, and we're still suffering from that. But for the other ones, basically you make the best measurement of the constant that you can in the old system, and then you define that constant to be that best measurement to make the new system. Okay, what do we have next?
First of all, thanks for the talk. It was very amazing. I have a question about the time, actually. When everything we said today, the definition of other measurements comes from time. We can measure frequency. My question is, without the definition of second, a standard for measuring time, how do we compare the different frequencies of lasers in a very good way? I don't know if a lame question, it makes a little sense.
Okay, Vanderlei, did you understand that? Because with the mask on, it was hard for me to understand. But if Vanderlei understood it, he can just tell me.
Okay, he wants to know. We use time for almost everything. So how we measure the frequency of the laser, if we have to use, we use the frequency to define the time. So how we measure really the frequency of a laser using what? Oh, you have your own.
Right, I have my own. Okay. Come to Dave Wineland's talk on Thursday morning, I think, and he'll explain a lot about this, but I'll just give you a brief explanation. So today, we use microwaves because cesium is the definition of time, and then we have to compare the frequency of the laser to the frequency of the microwaves. And today, there is a relatively easy way of doing that. You get what's called a frequency comb. You have a laser that puts out pulses of light. And those pulses of light are very evenly spaced. And that produces what's called a frequency spectrum. That is, the distribution of frequencies coming out are also evenly spaced, and that's what we call the frequency comb. And what we do is we compare the difference between one frequency and the next frequency to the microwave frequency, okay? And then, with some other tricks, we know that the laser frequency is an exact multiple of that spacing between the frequencies. And so, in that way, you can determine what the frequency of the laser is. But Dave will give you a much better explanation of that if you come on Thursday.
First of all, thank you, Professor, for coming and for the talk. It was great. And my question is, when you said we don't have a second-order Doppler-free technique, you mean it as in it's impossible, it can't happen, or as in we don't know of one?
Well, as far as I know, it's impossible. But of course, you know, you can't know what you don't know. But because of the fact that that the second-order Doppler goes like the square of the velocity, then whether the velocity is positive or negative, I get the same result. Whereas with the Doppler shift, it goes like the velocity itself, and that means that when I change the sign of the velocity, the sign of the Doppler shift changes, and that way I can make it cancel out. And there's no way that I can make the second-order Doppler shift, which people would also call the relativistic time dilation. There's no way that I can make that cancel out. But in principle, I could measure the velocities and make a correction, but it's hard to do that, and so the best thing to do is to make it really small. Now, for some of the experiments that Dave does with the ions, they actually need to make that correction to the because of the motion of the ion in the trap, and well, at parts in 10 to the 18 or parts in 10 to the 19, you have to include everything.
Thank you for your presentation. I want to ask about a prior topic about how get atoms colder, yeah, using light.
Yeah.
The way I think classically is that the atom has some kind of frequency. In this, you define its temperature. Then you launch a light on it with a certain frequency, right? Then you need a certain frequency to not get the atom hotter, yeah? Like if you get too high of frequency, you cause the atom to get hotter, not colder. I wanted to talk about how exactly we know the frequency you need to launch in the atom. And two, about what exactly was wrong about our assumptions to get other experimental results with the temperature.
Yeah. Okay, so the frequency of the atom, that is the frequency of light that it likes to absorb, is not very strongly connected to its temperature. The center of mass motion of the atom doesn't change what that frequency is, especially if you stay in the rest frame of the atom. That is, if you move along with the atom, then having the atom move doesn't change a thing. We will always cool the atom down if the light that is absorbed is going in the opposite direction from the way the atom is going. It won't matter what the frequency is, it'll always slow the atom down if it's absorbed from the laser that's going in the opposite direction. Now, the beauty of the whole Doppler cooling scheme is that you can favor the absorption from that good direction because of the Doppler shift. You make the frequency of the light a little bit lower than what the atom would absorb if the atom were at rest. And only when the atom is moving toward the light, which is to say opposite in the direction from the way the light is going, will the Doppler shift compensate for the fact that you detuned it a little bit lower. Now, if you were to detune the laser so that it was higher than the frequency, then you would heat it. Everything would work the same way, it'd just be the opposite, and you'd heat the atoms. But as long as you tune the laser below what we call the resonant frequency of the atoms that they like to absorb if they're at rest, as long as it's below that, then you will cool the atoms. Does that make sense? Okay, good. Yeah, so the question is, how did the community react to the change in the definition of the units, and how long did it take? Well, decades is how long it took. That is, people started to talk about this in the latter part of the 20th century. And it literally took decades before people accepted that this would be a good way of doing things. And even when they accepted that we should do things this way, it wasn't clear what we should do. What we did was define Planck's constant and the charge on the electron. But some people said what we should do is to define the Josephson constant, 2e over h, and the von Klitzing constant, h over e squared. That would have been equivalent, but and it would have made more sense from a metrological point of view. That is, the things we use every day to measure electrical quantities would have been a terminating 8-digit number or whatever. But instead, it seemed like it was more philosophically beautiful to define Planck's constant and the charge on the electron. But it took a lot of international discussion to make that happen. And as you can see, the definition of the meter came in 1960 in terms of the wavelength of krypton, when the new meter was made in something like 1790. So that was 70 years that it took to change that definition. Takes a long time. The metrology community is very conservative.
Okay, is the girl here? Yeah, stand up. And then the two guys that are with the hands up from the beginning of the talk. You and the other one asked for a help, so the friend is holding his arm.
Okay, is your hearing a little better than mine? So that's the trouble when you get old and your hearing goes.
A medida modifica a frequência. Okay, she wants to know if the velocity of the atoms modify the velocity of the light. Answer is no. Velocity of the light is a number. It's defined that maybe we didn't have the ultimate measurement, but up to now we say we have good enough to define.
So,
It is more or less.
yeah, more or less that's true. The velocity of light in vacuum is a constant, and it doesn't change depending upon how you look at it. Now, the trouble is, of course, if there are a lot of atoms around, then you would have the velocity of light changed by effective index or refraction of the atoms. But in most cases, that's not a problem.
Loud.
Professor, congratulations for the presentation. And my question is about the precision of the cesium clock. Like, it's too much precise, and we know about it. But for example, it causes like the magnetic field of the Earth causes like it changes, and how we can like correct this? How we
Yeah.
manage this?
Yeah, so the magnetic field is an excellent example of the kind of thing that happens. So what you do is you measure what the magnetic field is by measuring a different transition. Now, I've made this a little bit too simple. I said there were two states where the electron was pointing this way and that way. Now, that's not quite right. It turns out that these two states are what are called hyperfine states, and each of those states has a slightly different energy in a magnetic field. So if I take, say, this hyperfine state and then change its angle with respect to the magnetic field, that changes a little bit too. And you can measure that as well. And that can give you a measure of what the magnetic field is. So you can either measure the magnetic field and then calculate how much that shifts the clock, or you can deliberately change the magnetic field and extrapolate down to field equals 0. And people use both of those methods to determine what the magnetic field shift is. So that one turns out to be relatively easy. The hard ones are things like the black body radiation, the thermal radiation. That's hard because the calculation is hard, and it's hard to change the temperature. But that's where all the work comes. That's why these people are star metrologists, because they worry about the smallest little effects.
Okay.
Yeah. So first, let me just clarify the idea. We're not measuring the angle between the photon and the electron. What we're measuring is what the frequency of a particular transition is between two energy states, and those energy states just happen to have to do with the orientation of the electron. But basically, we're measuring energy states, and we could It could be any energy states. It just happens that for cesium, it has to do with the orientation of the electron. Now, your question was whether the interaction between the atoms will affect things, and the answer is yes. When the atoms collide with each other, it changes the wave function of the electron a little bit, and that changes the hyperfine frequency a little bit. Now, the way in which we deal with that is we make measurements at different densities of atoms. Now, the typical density of the atoms is 1 million atoms per cubic centimeter. That may sound like a lot, but most people would call that a really good vacuum. So what we do is we measure the frequency as you change what that density is. Now, the problem with that is that as you reduce the density, which gets closer to the no collision result, the signal becomes smaller, so it's harder to measure. So this is why it's hard to do these things. But with making those kinds of measurements, that's how they get rid of that effect, and the degree to which they can't get rid of that effect is one of the things that affects the uncertainty. Now, with optical frequency standards, I didn't really talk about what the new frequency standards are going to be. They're not going to be microwave. They're going to be at optical frequencies. So instead of being 10 to the 10 hertz approximately, it's going to be more like 10 to the 15 hertz. And that means a lot of things are not going to be a problem. But collisions, as it turns out, are still a problem, and, but at a part in 10 to the 18 level, not at a part in 10 to the 16 level.
No, wait. We have a question from one Nobel to the other Nobel. Let's see how that goes.
I hope this is interesting to the students, but how did you become interested in physics, Bill?
How did I become interested in physics? Well, I have been interested in science for about as long as I can remember, or perhaps even longer than I can remember. So I've sort of made up stories. One of the stories is that my parents gave me a microscope when I was 5 years old. And I used that microscope to look at all kinds of things. And there are kits for adventures in science that include microscopes that I hope are going to do the same kind of thing for kids today. But I was always curious about everything when I was a kid. And I think that I had the great good fortune that neither my parents nor my teachers were able to squeeze that curiosity out of me. And as time went on, I understood that curiosity about nature was really about science. And in science, there was biology, and there was chemistry, and there was physics. And chemistry was sort of smelly, and biology was sort of icky, and physics was nice and clean. And now another thing is that I have a very bad memory. And in chemistry, I would have to remember all kinds of things about what atoms react with other atoms, and what atoms have a higher electronegativity than other atoms that would determine how compounds would be, and you'd have to memorize that whole periodic chart. And I couldn't do that because I don't have a good memory. And in biology, you had to memorize the names of all kinds of organisms, you know, the genus and the species, and I couldn't do that. In physics, you just have to remember a few equations and a lot of math, and it's all there. You just work it out. I don't have to remember how far something goes in a certain length of time with a certain acceleration. I can just integrate Newton's law, and I get the answer. So that was a lot more appealing to me because I have a bad memory. So those are the stories. But remember, they're sort of stories about a time that I don't remember all that well. I do remember reading books about physics. I remember reading a biography of Marie Curie, and I was just so fascinated by this story of Marie Curie and her sort of lifelong adventure in separating out radioactive elements, and it would just seem so romantic and compelling to me. And I remember reading other books about physics, and I think it was those books that really solidified my interest in physics. One of the great books was one by George Gamow called 30 Years That Shook Physics, about the development of quantum mechanics, and now I'm a quantum mechanic.
Okay, look. Everybody knows the vice director, and before we continue, she wants to thank you, the two researchers, to be here. So, Ana Paula.
Thank you very, very much. I never ever seen the auditorium like this. It's the first time that I saw so many people in the ground. It's a pleasure, a great pleasure for us to have you here, to see your talk. It's wonderful. Thank you very much. I am sure that tomorrow will be like this. I hope so, to see all you here again. And thank you very much.
Well, thank you. It's been a pleasure.
We did not finish yet. We did not finish. You see, everybody has good questions, and Bill is a lovely person, and he likes to stay close to the students and talk. And all of you that has a question, we're gonna hang around so you can ask in personally your question, okay? Before we ended this, I want to say that this was a tremendous audience, maybe one of the most motivating audience we have here, so thank you. Tomorrow we have David Weiland. You know, I think David is a very quiet person, but he was one of the seminal persons in all the field of laser cooling. You agree with that?
In 1978, he did the first laser cooling of ions, and when I read that paper, I thought, wow. Let's do that with neutral atoms.
Yeah, but
and it took me a long time before I...
Yeah, and he did the fundamental experiments to really push the quantum computation. The quantum operations that are logic processors that will eventually end with a full revolution in the way we deal with data. So I hope you all come tomorrow, and there will be a surprise. Today you only got the presents of Bill. Tomorrow everybody that comes will get a present. But because I don't know exactly what it is, uncertainties, we only gonna know tomorrow. So if you come tomorrow, we're gonna have a good time again with David. Ions, superposition, entanglement, all those words that we hear in the TV, but maybe it's a good idea to hear from the guy that starts, right? So it will be a wonderful time. Bill, you want to say something else before we let the people invade the...
Well, I'm just wondering, first of all, I'm amazed that there are so many people here and that you didn't leave when the talk lasted more than an hour. I mean, you've been here now for more than 2 hours, a lot of you. And I think it's absolutely amazing that you've found this little bit of physics to be that interesting. I'm just so happy to see people who are interested in physics like this. What's the best way of doing this? Probably there are people who have to be someplace, and we should let them go. But maybe the thing is that everybody who's left comes closer and sits in the front. I think if everybody gathers around, we won't be able to have everybody hear the questions.
We're going to stay around. You are welcome to come. And Bill loves picture. When you take a picture with him, like this, it seems he changed. You know, the flash of the telephones and the camera makes Bill different. And if you have a picture with Bill, it's the beginning of success. So, do it. I was going to put him in the middle and take a picture with everybody, just thinking that maybe we could have a collective success. You think that works? Many body physics? It may, right? So we can try. But I'm going to let you first take a picture. And tomorrow, we're going to try to go out and take a giant picture all together. Okay? Look, this audience was marvelous. Thank you very much. You know why we put on December, not on the Semana da Física? Because we want to be a Christmas present, bringing people that you can talk and they are nice. You can even drink a Coca with Bill, and he loves Coca-Cola. Me too. I'm trying to convince him to move to Pepsi Cola. Change, but okay. Thank you very much. The ones that want to stay, ask a question, take a picture, get the prize. Lucas and Serginho, you help here, and Amilson is here too. So thank you very much. The ones that want to leave, please come back tomorrow, okay? And everybody's going to get a present tomorrow. And even taste is a present and taste. Looks and taste. So come back. Thank you very much.